Hello, physics class. We're going to continue with the ideal gas law because I've got a sample problem for you and a correction. Also, a video I'd like you to watch. But first up, let's talk about a mechanical device called a piston. So, a piston is a mechanical device in which you've got some sort of cylinder that neatly fits inside of another cylinder. This is a medicine syringe that you'd use to dose out kids' medicine, and you can see that obviously this part is an empty tube, and that part just is a circle that fits neatly within that tube. So this part is called a piston, and you can use it to force the contents of this out that opening. Now, because there is an opening, this is just moving air around, no differently than if I had taken it out and just, waved it around in the air. But inside here, this little bit of air is what's getting pushed. And because it's an open system, it means that the air pressure is always constant. So you can get an interesting effect if you block off one of the sides. I know this doesn't come across very well in video, but this is actually quite difficult to push. And if I let go, all of a sudden it just kind of bursts open. Anyway, so this is the kind of device that is going to be in the example. So just in case that is a helpful illustration for you, I'll bring it back when it's time. So here is here's the container we're going to have. We're going to make it cubical, so it's a lot easier to handle. So, or at least box. So let's go with my famous Mr. Estes geometrical art. That's all right. So this is going to be 10 centimeters by 10 centimeters by 22.4 centimeters. So just real quickly then, if volume is equal to length times width times height, and we want to do this in meters, we have 0.1 meters by 0.1 meters by 0.224 meters. And that means we have a total volume of 0.00224 cubic meters, which just happens to be 2.24 liters. Now, the reason that this number has been chosen is to make the math easier, because if you remember your stoichiometry, then you'd remember that 1 mole of gas at S, oh, that's not an S, that's a 2, at STP has a volume of 22.4 liters. Well, that's a tenth of that, which means that this box can contain a tenth of a mole of an ideal gas. Okay, so now that that's set up, I'm going to give you the correction to the ideal gas law. It's not exactly a correction because what I gave you last time wasn't wrong. It's just impractical. So PV equals nRT. The units for R that I gave you last time were joules per mole Kelvin. And the reason that that's impractical is because you want the units to cancel out. And while joules is an equivalent to this other side, it's based on pascals, which are a unit of pressure, which are kind of hard to use because air pressure is like 101,000 pascals. Yeah, that was a mistake. I should have given you a more basic one. So I have a correction for you on that. I have a new value of R that we're going to be using from here on out, and that would be R is equal to 0.08206, and the units for this are liter atmospheres per mole Kelvin. Liters is the unit of volume. Atmospheres will be the unit of pressure. And of course, temperatures in kelvins, and this is the number of moles. So the number represents the units that we're going to be using better. Sorry if it's going to throw you off from last time, but this is going to be the number we're going to use for R from here on out. And let's go ahead and get started. No reason to wait. Let's just make sure that that equation works for this scenario. So let's just start out with pressure at 1 atmosphere. That's just normal air pressure. We know what the volume is. It's 2.24 liters. Okay, now based on this knowledge, we know that this is 1/10 of a mole. So N is equal to 0.1 moles. And let's see, we've got R, and last of all, we need T. Now, this is at STP, standard temperature and pressure. And if you will just remember what STP is, that would be a pressure of 1 atmosphere and a temperature of 0 degrees Celsius. In kelvins, that is 273 kelvins. Okay, so let's just plug all these in, make sure everything works out. P V equals N. Oh boy, that number is going to be kind of big, and I'm going to run off frame. So I'm just going to stick R in here. R and then T. Just barely made it. Okay, so if you do the multiplication, obviously 1 times 2.24 is 2.24. And if you do 0.1 times 0.02806 times 273, you end up with 2.24. So in order to make these numbers and these units all work out, you just need to stick that number for R in there, and it equalizes everything. Okay, so now let's actually get to the part of this that is a physics problem. So you notice that the box I drew is kind of tall. What we're going to do is we're going to compress it. So let me get that set up for us. Let me draw the picture first of all. I think this will help. Unless my art is terrible. Ooh, like that. Then it will not help. Sure, that works, right? Okay, so just remember that the top here is a 10 centimeter by 10 centimeter square, and this is 22.4 centimeters tall. What's going to happen is this is going to get crunched down to half of its height. It is now only 11.2 centimeters tall. So if the height of this box has been cut in half, that means that the volume of the box has been cut in half. So if we are looking at this equation, PV equals nRT, and the volume goes down. Let's just remember this in terms of direct variation and indirect variation. If this side all stayed the same, then the pressure would have to go up. However, if this side stayed all the same, then the temperature would have to go down. Now, if both sides change, then this just gets really, really complicated. So what we're going to do is forget about all that. We're just going to say that the process is complex. If you want to deal with the process, and you're going to have to do this with like calculus in like a sophomore level college thermodynamics class, we're just going to deal with the end result. And because we have a cylinder and a piston, if you change the volume, lots of stuff will happen immediately, but after a while, some things will return to normal. And because this kind of piston thing is going to be, in air, that means that eventually any temperature change is going to equalize. So we're going to operate under the assumption that eventually the temp will return to 273 Kelvin. Okay? Just imagine that you've got this cylinder in like a, some laboratory under controlled conditions, and you compress it and the temperature changes, but eventually the temperature returns to normal, because that's what happens when you have something that is a different temperature from the room. The temperature just returns to normal. So the only thing different after a while should be the pressure. I've made this so the math won't be too difficult, so hopefully you don't mind if I speed through it. If PV equals nRT, and the volume is now 1.12 liters, and everything over here is the same as it was before, well, the only number that can belong here would be 2. And that means, this maybe isn't even surprising to any of you, that if you've got some quantity of gas in a cylinder, and then you compress it to take up half the size, the pressure has doubled. Make sense? You can even, yeah. So that would be a result of that. You have gas that used to occupy a lot of space. It now occupies less space, and the pressure has gone up. There are devices that are capable of doing this. One example would be something that is in a lot of auto and mechanical shops: a compressor. If any of you have a compressor at home, you probably use it to fill up tires, or maybe if someone has some air tools in their garage, they use it to power those tools. Anyway, so we've got some compressed gas here. Well, this problem has a second stage here, because if I raise the pressure of this, I have to hold it. The reason being, if I let go, that's going to shoot back out, because there's a pressure imbalance. There's only 1 atmosphere of pressure on the outside, but there's 2 atmospheres of pressure on the inside. Let's say that pressure is released. What will happen then? I'm going to get another piece of paper for this. Okay, so new scenario. This box, 11.2 centimeters tall, but now we open the lid. and the gas is able to freely expand. What will happen then? Well, remember, we still only have 1.12 liters of gas. However, the pressure has just changed to 1 atmosphere because we've exposed it to the environment. What will happen now? Well, the pressure's not changing. I mean, that's the entire planet. You're not going to change the air pressure here. Obviously, the volume you can expect to change, but we're just talking about the instant after you open this. The pressure's gone down. The volume is about the same. There's only one other thing that's able to change, and that would be the temperature. So looking at it like this, PV equals nRT. The pressure is 1 atmosphere. The volume is 1.12 liters. It's still 0.1 moles. Sorry, that's a parenthesis. Looked a little too straight. That is 0.1 moles. R is the same. And now, what temperature? Well, just kind of like last time, we were able to work out what everything should be. If this is half of what it used to be, 1.12 instead of 2.24, the only way to make the math work out here, and you can solve this for yourself if you want to see, is for the temperature to drop to half of 273, which is 136.5 kelvins. That is brutally cold. That is negative 136.5 degrees Celsius, or if you prefer, it is negative 213.7 degrees Fahrenheit. If you have ever used or seen a can of compressed air, you will see that there is a frostbite warning on them. You are not supposed to spray yourself with compressed air because it comes out so cold that it can actually cause frostbite. One game I remember Mr. E doing in physics years ago was put some water out on the table and then just spray it with compressed air. You can actually just watch it freeze. It's absolutely ludicrous how cold that comes out, but here's the reason why. Okay, you start out with gas in some state. Everything is in equilibrium, it's fine. Then you have to do some work on it. You do some work, and what ends up happening is that work has to express itself in some physical form. The work can express itself as a change in pressure, or a change in volume, or a change in temperature. Basically, the physicality of whatever it is that you're doing the work on is going to determine which of those is the change. A piston is good at changing pressure because temperature can flow through it. Now, if you've done work and that's resulted in a change in temperature, but then you allow that temperature difference to equalize, you end up with a sample of gas that has less energy than it had originally because you did work, it changed some of that energy into heat, and that heat was able to leave. Okay, so the amount of energy in this container is less than the amount of energy in this container because some of it left as heat. Once the pressure is released on this, then you end up with this being very, very cold. Okay, this this leads to a conclusion that I'd like to give you a calculation for. In order to make this simple, I had to look up the molar specific heat of air. Not useful to measure the mass of air in this situation because we never actually had a mass of it, we just had moles of it. So if you were to look up the specific heat of air, but the molar specific heat, you end up getting 29.07 joules per mole Kelvin. And if you plug in everything, we had 0.1 moles. It had a temperature change of negative 136.5 kelvins. And then we put in this number here, 29.07 joules per mole Kelvin. Let me just bring these crayons back for color coding. Moles cancels out. Kelvins cancels out. And we're left with joules. This is basically MC delta T, except M is moles instead of mass. So when you multiply these together, 0.1 times negative 136.5 times 29.05, you actually find that over the course of this process, this air lost 396.8 joules. That's how much energy was lost as heat here. Okay, so while this last slide is up, let me just talk about what this could be useful for, and then I'll tell you what comes next. So first, if you use a compressor to do some work on a piston like this, on something compressible where you have the opportunity to equalize temperature, you can actually use that to produce refrigeration. Now, if you will look in a very strange place, mind you, on the back of your refrigerator, you should see basically a radiator. The reason is because you need a way to get rid of the heat that you make when you compress something. Instead of compressing air, a refrigerator is compressing something called a refrigerant, which is basically a substance whose properties make it ideal for this application. Also that aren't really poisonous or something. So that is how air conditioners and refrigerators work, and it's why big air conditioners are so loud. It's because of the compressor inside of it. But this also means that you are able to use the compression and the expansion of gases to do work for you, or at least transform work for you. And really the only cost of it is that you produce a lot of waste heat. A good example of this would be an internal combustion engine. It works in a different order than this, of course, because what happens instead of a compressor is you have a chamber that is small, and then you are able to ignite a fire inside of it. And what happens is it expands that chamber, right? And so that needs to cool down so that it can compress again, and you end up with one complete cycle of internal combustion. So also in the links section on the LMS, there is a link to a video by the channel Smarter Every Day, and he built a transparent engine. I think he maybe replaced the head with acrylic or something so that you can see the inside of an internal combustion engine in slow motion. I just want you to watch that so you can kind of visualize how this process is actually used mechanically. And I'm just going to post a couple practice problems for you to do for homework. Anyway, yeah, there's your class. Yeah, there's your class.